Hello friends, welcome to my lecture on graphical method. So, let us see what is a linear programming. A linear programming is an important optimization, that is maximization or minimization technique used in decision making in business and everyday life for obtaining the maximum or minimum values as required of a linear expression subject to satisfying certain number of given linear restrictions. Now, the linear programming problem in general calls for optimizing, that is maximizing or minimizing a linear function of variables called the objective function subject to a set of linear equations and or linear inequations called the constraints or restrictions. A linear programming problem in short is written as LPP. Now, say mathematical description of a general linear programming problem. A general linear programming problem can be stated as, so this is a linear function, okay, which is to be maximized or minimized subject to the constants. So, these x1, x2, xn are subjected to these inequations, okay, a11 x1 plus a12 x2, a1 and xn. It could be less than or equal to, it could be equal to, it could be greater than or equal to b1, a21 x1, a22 x2, a2 and xn, and then less than or equal to greater than or equal to b2 and am1 x1, am2 x2, amn xn less than or equal to or greater than or equal to bm. Now, if there is equality here, then they are called equations. If there is inequality here, then they are known as inequations. So, the linear expression z equal to c1 x1 plus c2 x2 and so on cn xn is to be optimized, that is maximized or minimized subject to these equations or inequations. Linear equations are linear inequations. Now, and the non-negative restrictions, there is a restriction on the values of x1, x2, xn that they are all non-negative. Now, aii here, these coefficients a11, a12, a1n, a21, a2, a2n, am1, am2, amn, these coefficients a11, a12, amn and b1, b2, bm, c1, c2, cn, okay, they are constants, okay. aij, I varies from 1 to m and j varies from 1 to n, okay. They are constants along bj equal to bj where j runs from 1 to m, 1 to m, okay, and ci I equal to 1 to and so on up to n. So, aij's, bj's and ci's are all constants. xi's where I runs from 1 to n are all non-negative. So, these are non-negative restrictions and these are constants. x1, x2, xn are called variables. Now, the function z is called the objective function. We have to maximize or minimize this function. So, this is known as objective function. The conditions given in 2, okay, the conditions given in 2, these conditions are called as constants, okay, linear constants, and the conditions given in 3, these are called as non-negative restrictions on the linear programming problem. Now, this linear programming problem may be stated in matrix form. We can write it in matrix form z equal to cx, z equal to cx where c is x is your x1, x2, xn, c is c1, c2, cn, okay. So, z equal to cx, okay, z equal to cx and ax, a is equal to aij m by n, okay, x as we have seen x is equal to x1, x2, xn. So, ax will give you ax less than or equal to or greater than or equal to b, b is equal to the column vector b1, b2, there are m equations b1, b2, bm, okay. So, the b is a column vector, matrix, x is a column matrix, c is a row matrix, okay, and A is m by n matrix. Okay. So, A equal to Aij m by n is called the coefficient matrix of the LPP. C is row matrix, as we said, we call it a price vector, B is a column matrix which is called requirement vector, and X column matrix of variables. 0 is the null matrix of type n by 1. So, 0 is equal to n by 1 means 0 is of the type n rows. Okay. So, 0 0 0. So, this is n by 1 matrix. Now, let us see what do we mean by solution of a linear programming problem. A set of values of the variables x1, x2, xn satisfying the constants, that is the equations, linear equations or linear inequations given by 2, they are which are the constants, is called a solution of the linear programming problem. Okay. So, a set of values of the variables x1, x2, xn satisfying the constants and non-negative restrictions of a linear programming problem is called a feasible solution of the linear programming problem. So, the set of values of the variables x1, x2, xn which satisfy all the constants and also the non-negative restrictions, that is x1, x2, xn are all non-negative, that will be called a feasible solution of the linear programming problem. Now, a feasible solution of a linear programming problem is called optimal or optimum if it also optimizes, that is maximizes or minimizes, as the case may be, the objective function of the problem. So, a feasible solution of the linear programming problem will then be called optimal, okay, if it optimizes, that is maximizes or minimizes the objective function of the problem. Now, if the value of the objective function, can be increased or decreased indefinitely, okay, such a solution will be called unbounded solution. So, the graph or the solution set of a system of simultaneous linear inequations is the region, okay, containing the points x I which satisfy all the inequations of the given system simultaneously. Okay. So, we shall use the graphical method. So, we have to understand it very carefully. The graph or the solution set of a system of simultaneous linear inequations, okay, that is the values of the set of values of x by x1, x2, xn which satisfy the inequations, okay, which satisfy the inequations will determine this solution set, and that will be the graph, okay. So, which satisfy all the inequations of the given system simultaneously. Now, let us see in general we use the which are the methods that we use to solve a linear programming problem. First one is graphical method. If the objective function z is a function of two variables, let us consider two variables case, z equal to c1 x1 plus c2 x2. So, when z is a function of two variables only, then the problem can be solved by graphical method. Okay. A problem of three variables can also be solved by this method, but it is very complicated. Okay. So, when we have a problem of two variables, that is z is equal to c1 x1 plus c2 x2, we find the optimum value of z by using, we can find the optimum value of z by using the graphical method. Now, the LPP having more than two variables, if there is a case where z is a function of more than two variables, okay, then we do not use graphical method, as we have seen. Even for three variables it is quite complicated. So, even the problem of three variables becomes complicated. So, in such cases the analytical method, which is also called trial and error method, is useful. Now, simplex method. This method is the most powerful method to solve a linear programming problem. Any problem can be solved by this method, and this method is an algebraic procedure which progressively approaches the optimal solution, as we shall see. Now, graphical method to solve a linear programming problem. There are two techniques to solve a LPP by graphical method. Okay. One is the corner point method, the other one is isoprofit or isocost method. So, what is corner point method? in this method we first obtain the region, okay, we first obtain the region in the xy plane containing all points that simultaneously satisfy all constraints including non-negative restrictions. Okay. So, we have the constraints given by the system of equations 2, okay, and the non-negative restrictions, that is x 1, x 2, x n are all greater than or equal to 0. So, we determine that region in the xy plane which is satisfied by all the constraints given by system 2 and the non-negative restrictions on the n variables x 1, x 2, x n. This polygonal region, it will be, we will see that it is a polygonal region. This polygonal region is called the convex polygon of the set of all feasible solutions of the linear programming problem. Okay. So, that polygonal region which is a convex set, okay, is the set of all feasible solutions of the linear programming problem, and this feasible, we call it feasible region or we call it permissible region. Okay. So, the feasible region or permissible region is obtained by finding the set which is set of values of x and y or x 1 and x 2 which satisfy all the constraints given in the given by the system 2 and the non-negative restrictions. Now, we determine the vertices of this convex polygon. So, the convex polygon, that is the feasible region that we have got, we determine the vertices of that feasible region. These vertices are called extreme points of the set of all feasible solutions of the linear programming problem. Okay. After obtaining the extreme points, once we have found the extreme points or we have located the corner points of the convex polygon, we will find the value of the objective function at all these extreme points. Okay. The point where the objective function attains its optimum value, that is maximum value or minimum value of z, okay, gives the optimal value of the given programming problem. Okay. So, we will determine the value of z at all the corner points, then whichever value is minimum will give us the optimum, that is minimum value of the given programming problem, or the corner point which gives us the maximum value of z, okay, will give us the optimum, that is maximum value of the given programming problem. So, it depends on the case the given function will obtain its optimum value, maximum or minimum, as the case may be, okay, by determining the value of z at all the corner points and then seeing which one is less or which one is maximum. Now, if the two vertices of the convex polygon, suppose there may be a case where two vertices of the convex polygon give the same optimal value, okay, of the objective function, then all points lying on the line segment joining these two vertices give the optimal value of the objective function. So, if there are two vertices of the convex polygon at which the value of z comes out to be same, then all points lying on the line segment joining the two vertices, okay, they will all be giving the optimal value of the objective function. So, in that case we say that LPP has infinite number of optimal solutions. What is isoprofit isocost method? To determine the vertex of the polygon region which gives the optimal value of the objective function z, what we can do is we draw a straight line in the feasible region corresponding to the equation obtained by giving some convenient value to k, say z equal to suppose c 1 x 1 plus c 2 x 2. Okay. Then we can consider z equal to k, that is c 1 x 1 plus c 2 x 2 equal to k, k is a constant. We draw this line, okay, we draw this straight line in the feasible region. This straight line is drawn in the feasible region, okay, which is obtained by giving some convenient value k to the objective function. This line is called isoprofit or isocost line, isoprofit or isocost line. Okay. Since every point within the permissible region on this line will yield the same value of k. Now, every point on this line within the permissible region will have same value k, because k is a constant. So, whatever points x 1 x 2 lie on this line, okay, c 1 x 1 plus c 2 x 2 equal to k means they will all have the same, give the same value of z, that is k. Now, we can also take k equal to 0. Now, it makes the determination of the optimum value of z easier if we choose k equal to 0. So, if we choose k equal to 0, then we will have C 1 x 1 plus C 2 x 2 equal to 0. That means, it will give a line passing through the origin and parallel to the isoprofit line. Okay. So, take k equal to 0, draw the line passing through the origin, okay. The line C 1 x 1 plus C 2 x 2 equal to 0, that will be isoprofit line or isocost line parallel to that will be a line, this will be a line parallel to the isocost or isoprofit line. Because isocost or isoprofit line is the one which is drawn in the feasible region, okay, having the value k. It is C 1 x 1 plus C 2 x 2 equal to k. So, if you draw the line C 1 x 1 plus C 2 x 2 equal to 0, then this line has the same slope as the line this one isoprofit line. So, they are parallel. So, this line is a line which is passing through the origin and is parallel to the isoprofit or isocost line. Now, we draw the lines parallel to this line, okay, over the permissible region. So, what we will do is, so now we will draw lines parallel to this line. Okay. So, this is, suppose this is line, suppose this line is C 1 x 1 plus C 2 x 2 equal to 0, okay, and this is your feasible region. Say let us draw a rough figure. Suppose this kind of figure we have, okay. Then we will draw lines parallel to this line, okay, and parallel to this line. So, what will happen? Now, we draw lines parallel to this line over the permissible region. If the objective function z is to be maximized, then the parallel lines are drawn in the increasing direction away from the origin till it passes through a vertex of the polygon and its distance from the origin is maximum. So, if we want to find the maximum value, of z, then we will go on drawing these lines till it passes through a vertex, this one, okay, till it passes through a vertex. This vertex is the farthest from the origin. The distance of this line from the origin must be greatest, the maximum, okay, till it passes through a vertex of the polygon and its distance of the line from the origin must be maximum. If the parallel line is drawn further away from the origin, then this line will not intersect the feasible region. So, if you draw the line further away like this, okay, then it will not intersect the feasible region if you draw a line further away from the origin. So, now the coordinates of this vertex will give the maximum value of the objective function. So, this vertex, okay, the coordinates of this vertex, this line which is parallel to the isoprofit or which is parallel to the line C 1 x 1 plus C 2 x 2 equal to 0 and has at the maximum distance from the origin, okay. This vertex will then give us the point at which we will have the maximum value of z. So, we will put the coordinates of this point in the given expression of z equal to C 1 x 1 plus C 2 x 2, we will have the maximum value of z. Now, if the objective function is to be minimized, if we want to minimize, then the parallel lines are drawn towards the origin till it passes through the vertex whose distance from the origin is minimum. So, we will, in this case, what we will do, let us say this is your C 1 x 1 plus C 2 x 2 equal to 0 and the region is this. Okay. Then we go on drawing lines parallel to this this line C1 x1 plus C2 x2. Okay. So, the line whose distance from the origin is minimum, this line, okay, this line is passing through the vertex, okay, through this vertex, and its distance from the origin is minimum. Okay. So, this vertex will then give us the minimum value of z. We put the coordinates of this vertex in the given expression of z equal to C1 x1 plus C2 x2 to get the minimum value of the objective function z. This is called as iso-cost or iso-profit method. Now, in case this line passing through in the case of maximum or minimum, if this line, okay, which has maximum or minimum distance from the origin passes through two or more vertices of convex polygon, okay, then each point on the line segment between these two vertices in the permissible region give the optimal value of the objective function. Okay. And in this case we say that the problem has infinite solutions. So, here what may happen that this line, say for example, in the case of minimum it passes through two vertices, okay, then every point on this line will give the minimum value of z, and we will have infinite number of solutions. Similarly, if this line parallel to the line C1 x1 plus C2 x2 equal to 0 passes through the point this one, okay, where the distance of this line will be maximum from the origin, then if again two vertices on for two vertices we have this line passes through two vertices, this one, this line like this passes through two vertices, then we will again have infinite number of solutions, because every point on that line will give us the maximum value of z. Now, consider this case, we have z equal to 20 x1 plus 10 x2, and we have these constants x1 plus 2 x2 less than or equal to 40. So, we are given inequations, three inequations are there, okay, and we are given z equal to 20 x1 plus 10 x2, x1 x2 are bigger than or equal to 0. Let us see how we can apply the graphical method to determine solution to this problem. So, what we will do, we will draw the lines, straight lines given by x1 plus 2 x2 equal to 40, 3 x1 plus x2 equal to 30, 4 x1 plus 3 x2 equal to 60, and from there and the non-negative restrictions x1 x2 greater than or equal to 0, we will find the permissible region to determine the minimum value of z. Now, let us see. So, this is the figure. Okay. We consider three lines x1 plus 2 x2 equal to 40. So, this is x1 plus 2 x2 equal to 40, this line. Okay. Then there is then consider the line 3 x1 plus x2 equal to 30, 3 x1 plus x2 equal to 30. So, this is 3 x1 plus x2 equal to 30. Okay. Then consider 4 x1 plus 3 x2 equal to 60, 4 x1, this is 4 x1 plus 3 x2 equal to 60. And when you draw these three lines, then the region which satisfies all the three inequalities, okay, this and also the non-negative restrictions x1 x2 greater than or equal to 0 is this region, okay, this one shown by dots, okay, this region is satisfied by those inequalities, all those inequalities satisfy this region. Okay. So, every point x1 x2 in this dotted region satisfies those inequalities and the non-negative restrictions. Now, what we will do, let us locate the vertices of this convex polygon. This is convex polygon. Okay. So, vertices of this convex polygon are, this is 40 0, the intersection of x1 plus 2 x2 equal to 40 and this line, okay, that is x1 axis. Okay. On the x1 axis x2 equal to 0, so x1 equal to 40. So, this 40 0 point, and here this line is 4 x1 plus 3 x2 equal to 0. So, x2 equal to 0. So, 4 x1 is equal to 60. So, x1 equal to 15. So, this 15 0 point, and then when you consider the intersection point of 3 x1 plus x2 equal to 30, that is this line and this line x1 plus 2 x2 equal to 40, you can solve, you will get the intersection point as 418. Okay. And then the intersection point of 4 of x 1 plus 3 x 2 equal to 60, that is this line and this line 3 x 1 plus x 2 equal to 30, this line, okay, that is this one. This has coordinates 6 12. So, 6 12 is the intersection of lies on 3 x 1 plus x 2 equal to 30 and 4 x 1 plus 3 x 2 equal to 60. Okay. So, intersection of these two is the point R, that is 6 12. Okay. So, we have found the vertices of the convex polygon. Convex polygon is your S P Q R S, S P Q S S P Q R S. Okay. This convex polygon, okay, are feasible region. So, the vertices are P, okay, Q, okay, R, and we have S. Now, at all these 4 vertices of the convex polygon, okay, we will determine the value of Z, okay, and see which value of Z is minimum. So, let us see. P is 40 0, Q is 418, R is 612, S is 15 0. The value of Z comes out to be Z is equal to 20 x 1 plus 10 x 2. Z is 800 for P, 260 for Q, and 240 for R, and 300 for 15 0. Okay. So, whichever is the least, okay, 260 is the least value. Okay. So, Z is minimum at the point 240 is the least value, 240 is the minimum value, and it occurs at the point 612. Okay. So, the Z is minimum at the point R, okay, and the optimal solution of the given LPP is Z occurs at is obtained at x 1 equal to 6 and x 2 equal to 12, and the minimum value of Z is 240. So, that is how we apply this corner point method. This is corner point method. Solution of this LPP by corner point method. Now, let us say we obtain the solution by the isoprophet method, then what we will do? We draw the line through the origin corresponding to Z equal to 0. So, you see this line, okay. This line is 20 x 1 plus 10 x 2 equal to 0, which means that x 1 2 x 1 plus x 2 equal to 0. Okay. So, this line is 2 x 1 plus x 2 equal to 0. And then we draw lines parallel to this 2 x 1 plus x 2 equal to 0, this line, this line, this line, and then this line. Okay. This line is at the has the minimum distance from the origin and passes through 612 point. Okay. So, the point 612, okay, will give us the minimum value here. Okay. So, the dotted line through the origin is shown in the figure. Drawing parallel lines from away from the origin, we see that the nearest line, okay, it is a minimization problem. So, the nearest line in the permissible region passes through the vertex 612. Therefore, the optimal solution is x 1 equal to 6, x 2 equal to 12, and minimum value of Z is 240. Now, let us take one more example. Suppose we consider we want to find the maximum value of Z equal to 2 x 1 plus 3 x 2 subject to these constants, okay, and the non-negative restrictions x 1 greater than or equal to 0, x 2 greater than or equal to 0. Then as in the case of the previous example, here also we consider the straight lines 2 x 1 plus x 2 equal to 5, x 1 minus x 2 equal to 1, and x 2 equal to 2, and then obtain the convex polygon. We locate the vertices of the convex polygon, okay, and then find the value of Z at all these vertices, and the value of Z for whichever vertex the value of Z is maximum, that vertex gives us the optimal value, that is maximum value of Z. So, let us see, we have the lines 2 x 1 plus x 2 equal to 5, this line is 2 x 1 plus x 2 equal to 5, this one, okay, and then we have x 1 minus x 2 equal to 2, x 1 minus x 2 equal to 1. So, this is x 1 minus x 2 equal to 1, this line, okay. And then we have x 2 equal to 2. So, we have x 2 equal to 2, this line is x 2 equal to 2, this one, okay. Now, let us see the region which is which the point x 1 x 2 which satisfy all the three inequations. So, that region is this one, dot shown as by dots here, okay. This region, okay, because x 2 is less than or equal to 2, x 2 is less than or equal to 2, okay, 2 x 1 plus x 2 is less than or equal to 5, okay, and then x 1 minus x 2 is less than or equal to 1, okay. So, this is the region, all right. Now, so we will have let us see which are the vertices here. This point, okay, this point is 0 2, because here this is one of the vertex of the polygon region. There are 5 vertices, 1 2 3 4 5, okay. This is 0 0, this is 1 0, because x 2 is 0 here on x 1 axis, okay, x 1 axis, x 2 is 0. So, this can be obtained, this point can be obtained by putting x 2 equal to 0 here. So, this is 1 0, and then this point is the intersection of x 1 minus x 2 equal to 1, this line and this line, 2 x 1 plus x 2 equal to 5. So, their intersection point is 2 1, that is q, and then x 2 equal to 2 and 2 x 1 plus x 2 equal to 5, that gives the intersection point r, 3 y 2 2, okay. And then we have this as 0 2, because x 2 is 2, x 1 is 0. So, now see, so p is 1 0, okay, q is 2 1, then you have r equal to 3 y 2 2, and we have s equal to 0 2 and o equal to 0 0. Z is equal to so OPQ, okay, RSO, that is the feasible region, okay. The values of Z at these points are, okay. So, values of Z are, let me see, Z equal to 2 x 1 plus 3 x 2, okay. Z equal to 2 x 1 plus 3 x 2. So, x 1 is 1 by x 2 is 0. So, this will be for this Z equal to 2, okay. For this Z is equal to 2 into 2 4, 4 plus 3 7, okay, and for this Z equal to 3 by 2 into 2. So, that is 3, and then 3 into 2. So, this is 9, okay, for 3 by 2 2, and 0 2 Z is equal to 0 here and 2 here. So, 6 here and Z equal to 0 here, okay. So, this value is the maximum of all these 5 values of Z, okay. And so, optimum, that is maximum value of Z occurs at 3 by 2 2, this point, okay. So, the maximum value of Z is 9, and it occurs at the point 3 by 2 2 by, if you use the corner point method, okay. So, by corner point method, x 1 equal to 3 by 2, x 2 equal to 2, and Z equal to 9. Now, let us see iso-cost or iso-profit method. So, draw the line 2 x 1 plus 3 x 2 equal to 0, okay. So, 2 x 1 plus 3 x 2 equal to 0, that is this line is 2 x 1 plus 3 x 2 equal to 0, and 2 x 1 plus 3 x 2 equal to 0 means 3 x 2 equal to minus 2 x 1. So, x 2 upon x 1, so x 2 upon x 1 is minus 3 over 2. So, slope of this line is minus 3 over 2, this line. Okay. Now, we go on drawing lines parallel to this line which passes through the origin with slope minus 3 by 2. So, this line, then this line, and we go on drawing lines, okay, till we reach a line which passes through this vertex, okay, which passes through this vertex. This line has maximum distance from the origin, okay, and is passing through this vertex. So, this vertex is the one which will give us the maximum value of z, and that at this vertex as 3 by 2 by 3 by 2 and 2 as we have seen gives us 9. So, maximum value of z is 9. So, here we have said the same, here we have written x 1 by x 2 is minus 3 by 2. Okay. So, yeah, so we have this slope is minus 2 by 3, not minus 1 3 by 2. Slope is minus 2 by 3. Slope is by upon x, na. So, slope is minus 2 by 3. Okay. Slope is minus 2 by 3. So, slope will be minus 2 by 3. Okay. The line corresponding to z equal to 0. This is the line corresponding to z equal to 0. Okay. It is shown by dotted line through O, which is parallel to the isoprofit line. Now, drawing parallel lines away from the origin, since it is a maximization problem shown by dotted lines, we see that the farthest line from the origin passes through the vertex R 3 by 2 2. Okay. If you draw lines parallel to the line 2 x 1 plus 3 x 2 equal to 0 even further, they will not cross the feasible region, therefore, they are not considered. So, we do not have to draw them. So, the farthest line from the origin passes through the vertex 3 by 2 2, hence the optimal solution is x 1 equal to 3 by 2, x 2 equal to 2 and maximum value of z is 9. So, this is how we solve a linear programming problem when z is a function of two variables by using graphical method. We can solve the problem by using corner point method and by using isocost or isoprofit method. We have shown that the two in the case of both the examples how to apply the corner point method and the isocost or isoprofit method. So, thank you very much for your attention.